So before actually I start that one, let me go to where I stopped yesterday. Okay.
Can we ask one question first?
Yes, exactly. Today is also gonna be like yesterday, so.
Okay. How do you record it? We wanted to record on our meeting on our group, and we don't know how to do that.
It's in principle. I mean, it's just there should be just like on the. If I am gonna. Okay. I'm just gonna stop sharing this and present my entire window. So here, normally, I think it's if you are using the same thing, maybe you may not have access. So you have to set up your own Google Meet to be able to record. If you are using the same link, it might not allow you because it requires, I think, maybe you need to have a Google Suite account. I don't think you are able to record it if you don't have a Google Suite account. So otherwise, it just should be there, like as simple as like click there and then stop and start. But I think I remember it's like if you don't have, I remember I think not everyone is able. You need to have like some kind of different account.
Okay.
So, yeah, that's probably the reason. I think you guys, if you want to record it, what you should do is maybe use Zoom or some others called Jitsi. That's also very easy. Yeah, but maybe Google Meet might not have recording if you don't have a different type of account. Okay, so I do that. So I am gonna just ask exactly people who haven't yesterday answered the question. Anyone who didn't understand this statement, this exercise, or yesterday, anyone who didn't answer yesterday, can you please just give me one example or the generalization version of this example? So when will that inequality satisfy? So can I just probably then select randomly Bessie? Are you there? Did you understand this part? Bessie Mukaria?
Hi, so sorry about that.
Hello?
Hi.
Hi. So the question is, yeah.
I didn't get that.
Okay. So this, okay. So just then I'll repeat it. Just at least at least there's one person who doesn't understand it. So the question is, there is this probability, like whenever we say probability of X or anything, in principle, even if it's not written, there is a background information I. So this is basically just a probability of X. Probability of X not equal to 0 and probability of Y not equal to 0. If that is the case, what are the examples that satisfy this condition, which is like if there are X and Y, like which is the probability of X given Y is greater than or equal to probability of X. So that's kind of when does this conditional probability becomes greater or equal to the probability of just one of it, basically in this case probability of X. So this, I said yesterday that this happens almost always when X, I mean, it's a necessary condition, because if Y doesn't matter, if X and Y are not correlated, then it's the equal sign. And if X and Y are correlated, that means knowing Y always maximizes the probability of X. So learning about y always kind of gives you more information about x. That's why this probability maximizes and therefore the greater sign. And yesterday we gave a couple of examples, summer and all that, but I will just give another example, which is, let's imagine that x is a gender and y being a body height. Now, if you ask for gender, then you will say like, okay, pick a person, one gives a higher probability of finding men than just picking any person, right? So picking a person among the taller ones. So this is y being the taller, like body height. So if you know that given a person is tall, and if you are asked what is the probability of being a man, then that basically just maximizes, because there is a correlation between being a man and being tall. And if you just get invert this thing, for example, if in this case x is being body height, then you might say like, okay, if the person is a woman, what is the probability of being tall? That's smaller compared to being, so this is exactly the kind of correlation means. Like when there is correlation, then whenever the condition is given, the probability increases. Okay, so again, this is kind of what yesterday I highlighted. Note that conditional probability represent logical connections, so correlations instead of causal ones. Okay, this hopefully you went through earlier this morning. It's about Bayes' theorem. Bayes' theorem is just basically uses the end rule. And yesterday I said there are only 4 rules in probability. And the end rule basically means probability of x and y, given some background information, can be given as probability of x given y times probability of y. It's the same thing if you just say probability of y given x times probability of x. So these two are equivalent because this x and y and y and x are the same. It's called symmetric. Okay, so that's why if you upgrade, because they are symmetric, if you write this thing twice with equal sign and then rearrange them, you get the base. So probability of x given y is equal to probability of y given x times probability of x divided by probability of y. So this is probability. This is kind of the general Bayes theorem. This is great. This thing becomes so powerful as soon as, of course, you label what x is, what y is, right? Let's imagine x is just like that. Let's imagine x is the parameters, a model, the model parameters, and y, let's imagine this is data. And if that is the case, and the background information, this I, let's say the background information is the model. So if you write it like that, then this thing has a name. So the Bayes theorem with this kind of symbols have because it's D means for data, theta is for parameters, M is for model. So this thing has a name that everybody is referring almost in every Bayesian thing. So one is called likelihood. This is basically a model of your data. So how your data is generated. It's trying to model the process, because in this case, theta becomes like the kind of the true theta that you are searching for. So given that there is a model in the universe, which is the model of the universe, or the model of whatever you are trying to generate. So for example, if it's a coronavirus cases, so you assume there is some kind of model that is operating at the moment in society with certain number of parameters. Given that, of course, the data is generated. Of course, you don't know that. That's what you are searching for. But given that there is assuming there is that, then the data is generated. And theta, probability of theta given a model, it has no dependent on the data. So that means it's saying the prior. What is your information about this theta, about the parameter values? It can be theoretical. It can be, from previous experiments, all that, and then probability of D given M, there's no theta dependent. So it's kind of, as you could see, given it's another rule called marginalization. This is exactly like the kind of you are removing theta, let's say x and y, in this case theta and the model, you are removing model and parameters, you are marginalizing over the parameters. So that's basically kind of is, if you integrate over all parameters and then you're only comparing what is the probability of the data given the model, that becomes the evidence of the model. So that's, so now I will ask if there is any question, because this is, I know you don't have to understand, but any confusion, anything around here that you are kind of, you want to ask, I give you the opportunity.
Yeah, Bhavan?
Yes.
Can you elaborate more on the product rule?
Yeah.
I also have a second question on the Bayes theorem, but I will come back to that.
So it is a definition. So it's basically, there are the 4 rules. So the first rule is the sum rule, like how do you sum probability, random variables, so that probability. And the second rule is how do you make a product of it. So that's why if you are asking what is the probability of being, in the case of gender and height, what is the probability of being a man and tall, is very different from asking what is the probability of being a man given that the height is tall. Okay, so this is kind of like, it's asking what is the probability of being this and that. Like it's, so for example, the other way is that in terms of the example you gave, what is the probability of being cloudy and raining? That's kind of is saying like, it's a very different question than asking what is the probability of rain given it's cloudy. So that one is assuming, okay, it was kind of like cloudy and it's kind of, now you are asking the probability of rain. But this one, the probability of rain and cloudy, you are asking in the future. So what is the combination of rain while at the same time simultaneously being cloudy? So of course it's high, but and if you can ask like, what is the probability of rain and no cloud? That's basically what you sometimes find, like when you have a kind of the rain without a cloud, right? So that's smaller, but still there's no zero. So that's kind of what is the end condition is. So most of the time in parameter cases, you have multiple like these end cases, and you have to kind of convert them into like conditional one. So this the product rule converts some end connected random variables to some kind of conditional way. And now if there were like many, like 3, basically this will be x, y, and then this one will be z, and then you kind of convert that into again, and you apply the product rule again and again until you find all in this kind of format, which is the conditional format. And that's called hierarchical Bayesian model. We will not touch on that one, but that's what you form hierarchy. Is that kind of at least clear?
Yeah, it's clear now. But what's the intuition of the product rule? I mean, I get the syntax, but what's the intuition?
It is mathematics. It's like the same as asking what is 1 + 1, what is the intuition? It's basically how the mathematics, I mean, it's kind of how the product rule, it's axioms of the product rule. So these are axioms in mathematics. So this is the syntax, it's no philosophy. This applies anywhere. There is no philosophy behind it there. This is called syntax or the mathematics.
Okay, nice. All right.
So that's why in every mathematics, when you try to understand, you have to just make sure that you distinguish between a syntax and an interpretation. A syntax is basically an axiom. That's how the whole probability theory is defined by this. And we don't prove that. It's not given by a proof. It's kind of, that's how the mathematics operates. And then from this, you will use these axioms basically to then go on and kind of do all the other derivations. So Bayes' theorem is basically the application of the product rule in a symmetric way. Is that clear?
Yeah,
Anyone?
Yeah, it's clear now. I also have a second question. So when we say the probability of theta given D and M, like what are we talking about? What does that mean?
So theta in this case is parameter, like it contains many of the parameters. In our case, it will be for our challenge, theta contains lambda, the transmission rate, the recovery rate, and many other things. And M is the model, because we are using only one model, just like we call it a model. So and that is given a certain model, because you could have used, for example, one model is SIR, another model is SEIR. So this will represent one type of model, because you are modeling for one model, just the parameters inside that model. So it's kind of like object oriented, like you are looking at like one house and within that house. But you can ask, of course, you can also compare models exactly with the same rule. That's called model selection. Now you are saying like, okay, houses within an area and a compound. So that's kind of model selection. If a house is a model, then comparing houses becomes model comparison, what we call. But within a house, within that model, you can ask also, what are the number of tables in that house? So this parameter theta basically just will specify number of tables, number of chairs, number of whatever variables you give within the house. So that's the model parameter, it's called. And D is the observation, of course. Of course, you assume D's generate, the model is able to generate D. Otherwise, you can't do that. So you assume, okay, I have a model that generates the data, D. I observed the data, and the data is supposed to be generated by a model. And I'm comparing this, my model. Of course, I am assuming my model describes the universe or whatever, the reality model. So that's why you are measuring it. So is that clear, or am I confusing you?
Yeah, it's pretty clear. So it's like saying, what's the probability of finding the right parameters that correspond to this data and this model, right?
Yeah. So it's basically, of course, you are asking this. It's not the right thing. It's just saying any theta. So what is the probability of this theta, whatever. So of course, exactly, you have to assign that probability. Of course, this probability will be higher when the parameter becomes closer to what generates the data. So that's why you get a peak. So that's what, when you say, like when you then finally plot the estimated value, then where you have a higher probability is where the theta is the kind of what you call the right theta, or the right parameter.
Okay, but for the D, do we use just the training data, or
exactly? This is just data. Whatever your model is modeling. Okay. Your model is always assumes to model the data. So yeah, that's basically just, of course, the data you can transform it, whatever. It always depends on what the model it wants to describe. Of course, the data is with respect to that. So for example, in our case, we are going to use the cases, the COVID cases. In that case, the model has to be the right model for describing how people are infected. That's why we use the SIR. If you are using data that's called the date, so the number of days, then in that case, the model should be a model that describes, or that kind of quantifies how many people die in a day, which is SIR cannot tell you that. I mean, it can tell you through the kind of the recovery, but it's, the kind of removed, the R part in the SIR is removed, but removed contains both recovery and death. So you don't have model for that.
All right, thank you. It's clear now.
Okay. So I think it's important. So I will just give another 1 minute, 2 minutes, if anyone wants to have any question with that. Okay, so hopefully you have then a clarity, and I would have liked to tell you a little bit more of, okay, what, so the most important thing from Bayes' theorem is that whenever you ask what is the probability of my parameter given a data, that's called posterior. Why? It's because you have no idea in the first place about that. But you know about one thing, because you observed the data, of course you can ask, given if I give you a theta, let's say theta is like, you know, like some small number, then you can compute. This is computable. This part is likelihood is computable because you have the data and you can give me one single parameter value, and then I will tell you what that probability is, because my model really does that. My model actually is that given a data and given you know, a theta value, then I can compute through some kind of like, you know, by assuming certain probability distributions. So this is computable. So probability of theta, which is the prior, this is what you specify by hand. So your previous knowledge, your degree of belief on each of these theta. And then this is uncomputable because this one needs an integral. This is the integral of that. So it's kind of, this is usually for parameter estimation, we don't need it, fortunately. That's why we don't, but for model comparison, we need it. But this is the most important thing you need to define. Okay, so I think I will come, when you look at this thing, a distribution, that's kind of a probability of X, for example, that's really, and you know, most of the time you have to know what you're looking at. You know, it's like, what does this mean? What does this peak mean? And what does this flat means? It really is telling you, it's basically, it depends on which way of interpretation you look at. But almost always, of course, you are saying, oh, this is, yeah, like a peak basically means like there is more likely that, you know, if the reality is described by this thing, then there will be a point that if I generate enough, they will concentrate here, right? And this one is basically means like to get an X value that is coming from here is very small. That's what it's saying. So, but in a kind of Bayesian way, because we really assume that data is fixed, so what is distributed is not the data. The data is actually fixed. You have a data, but this is what it's called, the probability itself is distributed. So like your model, what you are trying, it's kind of, you are sampling that. And when you sample your model, it will be distributed like that. So it's your model, that's because it's posterior. Usually we look at posterior plots. So it's actually the values for your theta are distributed like that. So with a single one even point, you can actually plot this kind of distribution for a Bayesian approach. A frequentist is saying, when you look at this kind of density plot, what you really are saying is that, oh, like if you multiple times draw this X data, it will be, you will have more concentration, more frequency at this value. So it's kind of really telling you, frequency tells you like, if you draw a lot of times the data, which you can't, which you are not doing, it's saying like, oh, its density will be up there. While in frequency, it's saying, oh, single point, measure a single point, one draw. And then if you draw multiple values of the theta, then it will be like that. So that's called, this is a posterior look, this is a likelihood look. So when you look at the same thing, when you look at in frequency interpretation, this is a likelihood. While if you look at in the Bayesian way, this is posterior. If you don't understand what I said, don't worry, it doesn't matter. And then I go to the next, which is actually where I will start the today's presentation talk. And so yesterday we talked about, again, interrupt me, okay? So yesterday we talked about inductive reasoning. That is saying there are two types of, one is you specify an axiom, like the coin is fair, is an axiom, like you specified it. And then you say like, okay, what is the probability of 7 heads out of 10 tosses, 10 experiment? You compute it, nothing to do. It's really purely everything is specified. While inductive reasoning is like, you get a data which has like 7 tosses out of 10, 7 heads out of 10 tosses, and then you want to ask, is the coin fair? So actually, you want to infer about the fairness of the coin. So that's called inverse problem. You are inverting, and you want to know about the causes, what causes that. So it's called either inverse problem or, and these are most of the problems in science, I told you yesterday. And the type of problems that fall under these inverse problems are hypothesis testing. You observe something and you say like, oh, you observe some people clicks a blue button and a red button in a website, and now you want to know which one works better. So it's kind of like, this is a hypothesis testing. Parameter estimation, what we are going to talk, like you want to find out what are the best fit parameters for the model, and model comparison, so which we are coming. So these are all inductive reasoning or inverse problems. And so examples for hypothesis testing is that a group of patients, 2 groups of patients received, one group receiving a newly developed COVID-19 vaccine, for example, and your null hypothesis will say like, this group don't show any difference with respect to another group who received just a placebo injection. So that's your hypothesis, and you want to test that through by getting data. That's what now currently all the people that are doing vaccine development are doing. They develop something, they put people in 2 categories. One receives that, the other one doesn't, and then they will check if this is or not. And statistically, then they have to compute if the vaccine is good or not, right? Model parameter estimation. This is usually you are saying what are the best fitting values of the SIR model parameters. And if you are model selection, is that the SIR model with constant transmission rate, that's one model, and another, the same SIR model with time-dependent transmission parameter, that's another model. And now you want to compare which one is the best model for the data. So that's kind of model selection. Earlier, I gave you exactly the same example was like, if you are within a house, and the house being now a model, if you are asking, what are the probability of having a table below, 1 or 2, that's kind of model parameter. But now if you are like within a community, within a city, if you are asking about the model itself, like, okay, which building is kind of better, then that's kind of model selection. I mean, probably it's not a nice example, but that's this. I'm not going to repeat this. And you really have to know about this. This is the key and the most tricky, and you have to learn it again and again and again and again, because you will forget it. Even if when I say that, probably some of you will forget it after 1 or 2 slides, because it's very easy to forget that probability of X given Y is not the same as probability of Y given X. And the reason is, take this very, very known famous example, female and pregnant. Let X be a female and Y being pregnant, right? So if you say, what is the probability of pregnancy given it's a female? Of course, it's not every woman is pregnant. So it's kind of like, let's say it's about 0.3%. Now, if I ask you, what is the probability of being a female given that the person is pregnant? Then it's 1. Because it's like if someone is pregnant, definitely it's female. It's like, that's what we know. At least so far, we don't know anything else. So that's really, these 2 are absolutely different. And it's really, this is where the probability is non-intuitive, because, they look the same, but they are absolutely different. And sometimes female and pregnant, this is quite easy to see, but sometimes they are not. Like sometimes it's like data and theta. So this is like, it could be Y, could be X, could be theta, Y could be data. And one is posterior, the other one is likelihood. But for you, it just doesn't matter. One is, it's like probability of T given D versus probability of D given, theta. It looks the same, but absolutely different. Just for yourself, like really make sure you read it every day, or you kind of think about it every day for the next week if you can, because this is tricky. And the consistency of probability tells us that if you observe, even if you give the data, like let's say, instead of observing measuring like for all the dates for the SIR model, what we are doing now, instead of measuring from day 1 to now, today, for computing using all the data versus every day doing the analysis, the result should be the same. It doesn't change. So that's called the consistency of the theory. And so inference, I think we just talked about it. This is usually what you want to infer. And always, this is called rule number 1. Write what you want. Because if you don't write it like that, in this case, like it's called posterior, x is the data, theta is the parameter, you want to find that. Not the other way around. You don't want px given theta, because px given theta is a likelihood, which you can compute it. You don't need to do any inference, because so first rule, write it. And second rule, use Bayes' theorem to compute, like to kind of, because this was what you want, right? This is what I said. This is what you want. How do you compute it? Using Bayes' theorem, something given probability of x given theta, which you know already, like you can compute it. This is computable. This is not computable easily. This one is computable very easily. This one is what you specify by hand. It's called prior. This one, most of the time, you don't need it if you are doing parameter estimation. So it's kind of like you make something uncomputable to computable through Bayes' theorem. That's why Bayes' theorem is the most powerful theorem basically in all Bayesian analysis you do. That's what you do. This is the kind of the machine that converts uncomputable things to computable things. So that's Bayes' theorem as part why it's so powerful. I just said about it, so I'm not gonna do. And another thing, most of the time, probably when you're coming to probability theory, what you don't know is that what is called parameter space. Okay, a parameter space is really like the dimensions. Like everything is just like if you have a parameter that is has two parameters, it's called a two-dimensional parameter. If the parameter has like 100, it's called 100 dimension. So it's all dependent on the and everything. The more the dimension, the harder it is to actually, of course, fit. So this is just a summary that when the dimension increases on the y-axis, like as you go to bottom, the dimension increases, and as you go in the from left to right, what you get is basically what kind of model you are applying to that data. So in the first row, basically in the first column, you are applying linear modeling. So it's linear modeling usually means like it doesn't matter whether it's 100 dimension or linear regression usually means you are fitting linear models across. So if it is in 2D, it's a line. If it's in 3D, it's a plane. If it is in 4D, it's kind of hypercubes. It's called just blah blah. So it kind of continues. 100 dimensions, you do linear regression. It's just that it's linear across all the dimensions. It means. So that's what you do. It's kind of you just make a thing, and then when you do nonlinear modeling, that's where it's basically that's called spline or interpolation. That's still another types of that's another type of regression. So it's kind of you're doing regression at nonlinear regression on the, let's say this is 2-dimension. This is nonlinear regression in the 3D space. And then of course the space could be so complicated. So the data point could be very complicated. In that case, that's what is called, you need to sample. This is a very hard to sample because, how do you get all those peaks? It is what is really deep learning is good at. It's kind of, it doesn't care. Like that's why it's kind of, you need powerful methods. The more dimension you have, the more powerful the method has to be to kind of does a nice regression. And that's why usually we use, like in a smaller dimensions, we use regression, linear regression. But in higher dimension, we need to use a more complicated thing like Monte Carlo Markov chain to sample from. Okay, so that's what's really just because these are going to be hard spaces to kind of sample them using a mathematical regression model. So usually you use Monte Carlo methods, and also convex and non-convex optimization. Convex optimization means there's only one peak and one local minima. So it's basically you just start exploring and it's very easy to do. So this is very easy optimization. If you know your problem is convex, usually it means like, yeah, it has one global minima, so just whichever method you use, it's kind of easier, you will get it. You know, it's just only you're trying to maximize the number of steps to get there. But if it is non-convex, for most of life problems are non-convex, in that case you really need a very good optimizer to get the global minima or the global maxima. And this is exactly what the kind of like deep learning, whatever, are good at. When you just, it doesn't care about school, it doesn't care about you know, how complicated your surface is. This stochastic gradient descent using multiple data, it kind of samples and recovers, you know, the space nicely. So that's basically just to digression from our thing. Okay, so Monty Hall problem, that was what yesterday was raised. So this is a kind of a brain teaser. I ask you. So this is a show. This was inspired, you know, from a real show. You have 3 doors, and behind each of the are 2 goats and a car, a Ferrari. You know, so 3 doors, and they're all closed. They are all the same color. No, you can't see anything from outside of whatever is behind it. But behind 2 of the doors, you have 2 goats. And behind 1, you have a Ferrari. And of course, you as person who's rational, you want to get the Ferrari, right? Whoever wants the goat, then they are not going to participate in this program. But, you know, just that's the problem, that you want to, of course, you want to maximize to get the Ferrari. And then you choose, you get into a show, and then you open up the, like, so the Monty, the show person, will just ask you, choose a door, which you think is randomly, exactly like I asked you yesterday, choose my mom's birthday. So now you choose, let's call, you chose A, door A, you know, whichever you chose, let's label it A, and then the others B and C. All right. Now the Monty Hall, the game show host, will just say like, okay, he will examine the other doors. That means he knows what is behind B and C, and always opens one of the door which has a goat. You know, so it opens. Let's say that door that's opened is B. So he opens the door B, and it's in a goat. Inside it is a goat. And now he will ask you, will you stay with your choice, which is A, door A, or would you change to door C? And let's just make it nice, like who wants to keep their first choice and who wants to change. And why, of course. The interesting thing is why. Write in the chat, and you can, I will mention a name to give an explanation. Is the problem clear? I think today, is that because it's afternoon? Okay. I think the participation is quite, okay, so Lashore, so she would keep the first choice. So do you want to say why? Not sure. Just a gut feeling. Okay. Who else? Okay, Binyam would change, but I like just a random guess. But that's what it really is. The problem is trying to, you know, the brain teaser is in the probability lecture, right? The tutorial. So you should think that, of course, this must be related to what I'm saying, or what we talked yesterday. But it's nice. I like it. Okay. Okay, Janet, to me the question is not clear. So this is a kind of a game. So you go to a game which has 3 doors closed. Behind 2 of the doors, a goat, and the other one is a car. and so it just happens there, and then you will just say, you have to just guess which door contains a car, and then you say door A, let's say, and then the game show will just open one other door, the one not A, not the door that you said, but the door, one of the doors that you didn't say, and it shows you that behind that door, let's call it C, behind C there is a goat. Now he will ask you, will you change from A to B, or will you stay to A? Is that clear? Okay, so Rofia thinks she can't. Okay, after picking A, are you allowed to know what's behind it? No, you're not allowed to bribe Dave. So Janet, hopefully that the question is clear. It's just think of it 3 doors. You choose one, and then the person doesn't show you what you chose, but opens one other door that you didn't choose, and then in the one that is open, it's a goat. So now it will ask you again back, will you stick with your choice or will you change? Okay, Moakeli stays with my opinion because the probability of me being right has increased from 33 to 50%. Okay, I would analyze Monty's face change. That's great. That's called outside the box. But he's a game show. That's why we made him a game show host, because he's okay. Dave, he thinks it's also probability 50%. I will go with my instinct in this case. That's beautiful. Yesterday we did exactly the same, and still we had still today there are people 50-50. No, okay, great. But who wants to speak? I think it's because of the afternoon. Maybe people don't want to speak. Who wants to open up your mic? And so, okay, more Kelly, why do you think it's 50% now?
Hello?
Hello, yeah.
So he's removed the other one. So now you're left with 2 options. So it's increased from original, when you had 3 options, you had 33.3 recurring % of you being right. So since he's removed one, you are at 50-50.
Okay, so one person doesn't agree. Was that Binyam? Binyam, do you want to argue with that?
I said I'd change.
Yeah, exactly. Why would you change?
Yeah, because
Kelly says she doesn't change, right? Because she would stay with her opinion, which is the first door.
Yeah, as it was mentioned yesterday, originally when the options was 3 doors, we had a 33.3% chance of getting it right. But then when the game host opens a door and we know for sure that the thing in that door is a goat, I think that's the problem.
He's not opening the show for the one that you chose. It's for another one, just to be clear.
Yeah. He opened another door with a goat.
Yeah. Yes, exactly.
So now I know for sure it's one of the 2 doors. It's either the one I picked or the other one that has the car.
Yeah.
So now my probability, as we mentioned yesterday, the probability for the door that I picked stays the same, which is 33.3%.
Yeah.
And since the sum of the 2 probabilities should be equal to 100%, the rest, which is 66 point something percent, would go for the door that I didn't pick. So I'm gonna change my choice, and I'm gonna go with the higher probability, which is 66 point something percent.
Great, thank you. But now I just want the debate to go on. Who wants to counter-attack that? Who thinks Binyam's explanation is wrong? or who has changed their mind from their original thinking after hearing Biniam's explanation? Okay, Samuel also is in the. So Samuel, do you have? So Olushola, I think I'm not sure your answer. If you are sticking or not, but Samuel, do you have additional thing to say on top of what Biniam said? And okay, I think just for the sake of time, I think people are today quieter. For the sake of time, we have 10 minutes only. I think Biniam's explanation is exactly what I said, and it's the same, exactly the same question as guess my birthday. Because it's like, it's the same. Just now in this case, it's 3. In the other case was 365. And so it's obvious sometimes to make the problem kind of expand, make it extreme, such that you know, wow, like when it's extreme, of course, your gut also tells you to change. Like if I say, okay, guess my father's birthday, and then you guess someday, you know you are more likely to get it wrong. And then now I give you 2 other options, then it becomes obvious like that your first probability, your first guess must be really just nothing. And so the second one, given that I have prior information about what is right, is actually should influence exactly what it's the sum of the probability of between these 2 has to sum 1, and your first the probability that was assigned to you to your first choice didn't change because I didn't say anything about. So prior means I didn't tell you anything additional about your first choice. I only told you another prior on the ones that you didn't choose. So it's actually nothing has changed from the probability to the probability you guessed, but to everything else it has changed. The probability distribution has changed. So that's why you should always change when the thing is more than 2. That's again a very the page. Yeah. So that is the thing, and I think you have the same this slide in the Google Drive, so you can just go with yourself. So model selection, it is about comparing models, and so again I'm just gonna stick. So model comparison is so you have prior. Usually there are 2 models, M1 and M2. So sometimes you specify, let's imagine this is kind of a parameter on transmission rate, right? So you may have prior on here, and you may have the data indicating a lot more here, and then what is called the posterior basically is usually because it's a product, it will be in the middle. In the other model, this is prior that was specified, and the likelihood, and the posterior is kind of like there. And now you want to compare which model is correct given the data. And that's what's called model comparison. And in another way, for example, just in this Hubble expansion in the universe, you can consider Mr. A has a theory that has the velocity of galaxies as a function of r. It doesn't change. And then Mr. B has a theory that says the velocity of galaxies actually changes as a function of their distance from us. So, and he says P is equal to HR. Now, who should you believe? You have a data that you collected, just their distance and recession velocity and their distance. And in this case, basically what 0 means is that, okay, H is equal to 0, it's saying, versus H is not equal to 0. So that's what's called model A. Model A is a hypothesis, H is equal to 0, and model B is a hypothesis, H is not equal to 0. So now you're comparing. In that case, hypothesis testing and model comparison become similar. So the Bayesian approach to do this is very simple. So you have now 2 models. You write rule 1, which is write like what you want. So of course, what you want is the probability of a model given X is what you want. Earlier, usually it was the probability of the, in parameter estimation, what you want is the probability of the parameter given a data. In this case, because you are you're doing model comparison, what you are writing is probability of the model given the data, right? Then you apply Bayes' theorem and you get something, so which basically just after rearranging whatever, it becomes called a Bayes factor. Then you compute, this will be like, let's say what you measured from data, the probability of H given X, that was during for parameter estimation, and then this was the prior. And basically just like you compute the integral. This is what's kind of when you want to compute, when you want to do model comparison, you have to compute the sum. Integral basically means the sum of that. So you will get that, and then 2.2 becomes what is called the fraction, the difference, the evidence difference between, or the odd ratio basically, between model 1 and model 2. And we have some criteria. What is a strong model, a decisive model, or a substantial model? In this case, our model is substantial. So you kind of don't choose much. It's kind of, you say like, yeah, sure, I think Mr. B, both of them probably are okay, but Mr. A, Mr. B, who says the velocity, is depends on as a function of radius or the distance, kind of seems to be preferred, but not strongly. So that's what's really, when you say statistically, it's not really decisive, but kind of it's okay. So that's what a statistical inference is. So if it was a coin, it was like, was it fair? You say, maybe it's fair, but I think with some caveat. That's the kind of substantial means. So MCMC, I didn't manage to do. Time is running in 5 minutes. What it's saying is that whenever you want to do parameter estimates, if the number of parameters are 2, great. You can just kind of do it on a grid. So you can basically compute by looping, for looping, by double for looping. You kind of go across a range and you compute, and you basically get the values. So that's what's kind of, you get like, if there are 2 parameters, you compute them on a grid, and then you will say, where is actually the minimum or the maximum. That's what you want. But if you have now, if you have 6 parameters, then you're basically, and if you want 6 parameters, 20 pixels on each of the dimensions, 20 points in each of the dimensions, then the number of parameters you have to evaluate becomes, kind of 60 billion or 60 million. But if your model to compute takes 1 second even for evaluating, then you need about 1,200 days. So you can't do that usually. So that's why you need a different approach. And that's where MC Monte Carlo or Markov chain Monte Carlo comes. The difference between Monte Carlo and Markov chain Monte Carlo, for Monte Carlo, you just randomly sample, just random generation. You don't depend on the previous point. You just only generate, and then you generate each of them separately, independently. While for Markov chain Monte Carlo, you don't generate it in one go, you generate one, and then given that, it's called conditional. Given that you generate the next point, given that you generate the next point, that way they are correlated, but they kind of, with a smaller sample, you basically cover, because then you are optimizing at the same time, like to go which direction to go. So that's what's called Markov chain Monte Carlo. Markov chain is basically a chain that depends on the previous point. And Monte Carlo is the same Monte Carlo, which is random sampling. So it's a random sampling with dependence on the previous point. That's basically what's called Markov chain Monte Carlo. And there is something here, just like, even the sampling part, like the proposal into which direction you go, it's a kind of on its own a distribution. That's why in Monte Carlo, you just generate, there is one distribution. If it's Gaussian or uniform, from that you just generate a random and you see it. Then you see that it's fine for a small thing, but if it's double peak, you will not be able to get it. With that, with Markov chain, you kind of can explore the space, the parameter space better. I know I'm running fast, but you have to go, and probably we'll come back to this point later. So that's what's the difference. Read it just in the slide, and if you have question, we will discuss over Slack, and tomorrow we go over also. This is a general thing, but we will go specific to our problem, to our challenge tomorrow morning. Great. So I hope you have many questions that we will talk. So until then, just all, yeah. So all questions just we'll discuss via Slack. So Sebastian, you can stop the record. Yeah.
Sure.
Great. Thanks everyone.